Welcome back to our video module on statics. I'd like to continue our discussion of the second moment of inertia by drawing in a problem. Give me 1 second. Perfect. Here we have a fish tank. So last year I bought this fish tank and it's like 120 gallons. I mean, the thing is huge, and you know, it's all over here. It's huge. But what I've drawn here is just the corner section where the water in here, all the blue is all water, it comes out through this port, through this hole. And that's mostly for filtration, that type of thing. Now let's imagine that instead of the nice big hole, which I really have, I'm going to put a gate in there. I'm going to put like this door, and the door rotates about this hinge right here. All right, so if it kind of like swings back like that, if something pushes it back, but what it's really made for is, let's say it really wants to swing out this way. And you can imagine why, right? You have all this water pushing on the door. It's pushing, it has all this pressure, and it wants to open the door. Now we've covered problems like this before, but they've always been square doors. Now I want to take a time to say, well, what happens if we have a door that isn't a good size, or isn't an easy, simple size? What's really happening? Let's start off by writing down a couple items we know. First, we know that the force due to, we'll say pressure, is whatever the density is times the depth, gamma y, and in this case y is going down. Okay, great. And we can use that to find out how much force is being pushed against this area. We take a look at we want to take the sum of a whole bunch of forces, and that is simply the sum of, at each area, at each one of these small areas, a small force. Well, the small force is gamma y, the pressure. So we know that the total force, if we put this into an integral, is the sum of gamma y dA. This should look very familiar to you. Remember, the integral of y dA is simply q, is what we called it. So in this case, gamma q. Oh, and actually, you know, I'm gonna change the axis here so we're clear. That axis is x. Looks a little confusing otherwise. There we go. All right. Now that said, this tells us the magnitude of the force. We can find that easily enough. We have to integrate the area. We can find out the magnitude of the force. But what it does not tell us is, where is that force acting? In order to find where the force is acting, what we're going to do is we're going to try and find the moment about this hinge. So we're going to take, the moment about the hinge is the sum of lots of small moments, right? And the only place that we have those small moments are right down here. So the small moments are simply going to be the y value, here we go, times whatever the small force is at each of these small areas. Small force 1, small force 2, you get the idea. Well, we know enough, we can take this equation up here and plug it in, and we get the sum of y times, actually let's do it here. The small forces are gamma y, there I go again, times delta A. You've seen this before. We can write this as the sum of gamma y squared delta A. A good portion of that looks like the second moment, and in fact the moment about the hinge is going to be the density times the second moment, which we call I, about x, whatever this dA is. So we can see that here we have a second moment telling us where the force is acting. The second moment tells us, where is this F? Where is it being applied? And the first moment tells what is the F, how big is the force. So we can use both of these in conjunction to solve this tricky problem. Hope this clarifies the difference between the two and their usefulness, and we'll see you next round.